Hey guys, so this is part 2 of the DC Circuit Builder tutorial. In this um, video we're going to talk a little bit about the parallel circuit setup and walk you through what that circuit looks like and kind of hit on some of the key points that I want you to come away from this assignment with. So first of all, we want to construct our parallel circuit. So parallel circuit, we want a couple wires across here, and then put an ammeter next to the battery, and then a couple of wires. Actually, we just need 3 branches. And then if you follow along with the diagram, put in 3 resistors, and then we want to measure the current going through each of these branches, and then we want to connect them all into loops. And so hopefully you can see why these types of circuits are referred to as parallel. Compared to with a series circuit, you had everything going through one single loop. Here you have branches, so you have parallel branches of conductive paths that the charge can flow through. So not all charge goes through the same pathway, and so we want to think about what does that mean in terms of the circuit and the different variables. And so first of all, I want to point out, if you look at the potential, so again, we define zero potential here on the negative side of the battery, and remember that's arbitrary. And then it's a 9-volt battery, so 9 volt, it's going to give us a boost of or a lift of 9 volts. And so this part of the circuit is all at 9 volts, and then it goes through each of the resistors, and on the other side of all those resistors, you have a drop of 9 volts across each resistor. And so on the other side, that entire part of the circuit is at 0 volts, and that leads us back to the negative side of the battery. And so this is different than the series circuit, where each resistor experienced a different voltage drop. Here they all experience the same voltage drop, and so the voltage drop across each resistor is going to be equal. And so that's one thing that we want to point out. The other thing is, if you take a look at the current, and so we have here, if you notice the speed, look how slowly the current is flowing through each of the branches, but then how quickly it is near the battery. So before it branches, before this junction, and after this junction, you can see a difference in speed. And if we look at the ammeters, that makes sense, because the total current flowing into and out of the battery is 2.7 amps, and the current in each of the branches is 0.9 amps. And so I want you to think about, what is the connection between the current in the branches and the current before and after the branches split up here and after they all come together. And you can actually show that the current before coming out is the same as the current coming in, and that makes sense, because we know that charge is conserved. So that's one thing. What's happening with the total current versus the current in each of the branches. The other thing I want you to think about is the resistance. So we have the resistance in each of the resistors, and we can figure that out by Ohm's law. We have a 9 volt voltage drop, and we know the current coming through each of those resistors, and so 9 volts divided by 0.9 amps give us a resistance of what, about 10 ohms, and that would be the same for each of these. And then what I want you to think about is, what is the equivalent resistance of the entire circuit? If you look at the total potential and the total current, what, according to Ohm's law, what kind of resistance do we get using those, and how does that compare to each of the branches? When we had a series circuit, we talked about how you could take each of the individual resistances and add them up and get the total resistance. That's not the case here, and the pattern's also not particularly intuitive or obvious if you haven't thought about it before, or you haven't seen it worked out. So anyway, that's something to think about. And then of course we want to figure out how much power is being put into the circuit by the battery, and how much power is being taken out of the circuit by each of the resistors. And again, we use the power law for that. Power is current times potential. The last part of this that I want to show you is what happens when you disconnect parts of a circuit. So say we just have one loop. Now we have a simple series circuit, or a simple circuit rather, and the current flowing through the whole thing is 0.9 amps. If we put another resistor in parallel, look at what's happened to the current. So we've added a resistor, but the current has gone up, not down. Think about what would happen if you added a resistor in a series circuit. What would happen to the current? It's doubled. The current has doubled when we've added resistance, and that may be, we've talked about resistance as something that impedes the flow of current. Here's an example where something different is happening. And then if we add a third loop, now you can see we get back to our 2.7 amps, and again we've managed to increase the current by a factor of 3 from the original. And so if you think about this, so what this means is the more things you put in parallel, the more current flows through the entire circuit. And you think about this in terms of, like we talked about, fuses and surge protectors and things of that nature. And we talked about this in terms of current and fuse protectors and things like that. And so that'll be something for us to kind of think about. So we've talked about, if you add more things into a wall outlet or a surge protector, what effect does that have on the current that is flowing? And so that would be something that we can think about. Okay, so that is pretty much everything you need to complete the homework for the DC Circuit Builder on parallel circuits. I look forward to debriefing this with you on Monday. Thanks.